All right, there we go.
The atom is the simplest particle of an element. Also, a proton is a positively charged particle within the nucleus. Neutron is a neutral particle within the nucleus, and an electron is a negatively charged particle that orbits the nucleus. Protons and neutrons make up the nucleus of the atom, which is therefore positively charged. Next, we're going to talk about bonding energies, which were discovered by Albert Einstein. He decided that the magnitude of an element's bonding energy can be found by taking apart the protons that form the nucleus and applying a certain charge to them. The charge will then free them from one another. This process can be reversed by adding the same charge to both of them, which will cause the proton and neutron to rejoin.
Give like an example, like draw an example. It's really like 2 minutes.
Okay. Here's our nucleus, and it has protons, and then I'm going to do these for neutrons. And so he discovered that if you take out the protons, or take them apart, and then apply a certain charge to them, the charge will then free them from one another. So before they were all bound together, and then they come out and they are all free. The process can also be reversed by charge of both of them will cause the proton and neutron to rejoin together. So this process can be reversed. Each element has a different bonding energy. Next is nuclear structure. There are 2 basic models for this, and they are the liquid drop model and the shell model. Both models are based off of the Pauli exclusion principle, which states that no 2 nucleons of the same kind can be at the same state. Under the liquid drop model, it was discovered by George Gamow and was later proved by Niels Bohr and John Archibald Wheeler. The model states that the nucleus is like a drop of nuclear liquid. The fluid is made up of the same composition as the nucleus. So here's a drop of liquid, and it's made up of protons and neutrons. This model does not explain all the properties of the nucleus, therefore it is not widely accepted as an explanation for nuclear structure.
All right, I'm going to be telling you about the shell model. Now, the shell model is the more accepted version today by scientists because they feel that it more adequately explains the principles of nuclear structure more so than the liquid drop model and other models in the past. Now, the liquid shell model, just the shell model was developed by Mr. Bohr and Ben Modelson. It's kind of a fun fact. The developer of the shell model was actually the son of another scientist who studied nuclear structure and actually won a Nobel Prize for work that he did from his father. And I thought that was kind of interesting. But yeah, he was developed by Bohr and Modelson. Now, like I said earlier, the shell model is more widely used, mainly because it gives the principle of why electrons orbit the nucleus. And this theory also helps explain why some nuclei are bound more tightly than others are. Now, protons in the protons in the outermost shell are loosely bound to the nucleus if there are only a few protons in that shell. For example, if you have an element like hydrogen, you only have, you only got one proton and then one electron. So since there's only one right here, it can't be very tightly bound, and the shell model helps explain that. And this happens because it is the farthest away from the center of the nucleus. It's also the closest, but in this case it's also the farthest away. Nuclei with a full outer proton shell are more tightly bound and have a higher binding energy than other nuclei. So if we took a crazy element like something with a really high atomic number, let's just make up an element here. Our made up element, and it has an atomic number of 101. So basically, you would have a nucleus that contains 101 protons and 101 neutrons, plus 101 electrons, all on the outer shell orbiting on their own orbital levels. So this explains why they would have a higher binding energy. Hydrogen earlier has a binding energy of 2.23 million electron volts. Now each element has their different a different binding energy, but hydrogen's is the lowest because it only has to separate one proton and one neutron from the nucleus. But say something like this made-up element here would have a very high binding energy, and there's a table that goes through all of the binding energies, but since this is a made-up element, we obviously have no way to know what the binding energy of that would be. Now, when an electron goes from a higher energy level, radiation is released. So if this electron right here wants to go to another energy level, let's say it's on energy level, let's see, E level, say it's on E level 10, and that's not what they're called, obviously. But say it wants to go to E level 11, radiation will be released from the energy that it takes to go to the next level. In the smallest orbit, the electron will be the most stable, and minimal radiation will be released. So going back earlier to hydrogen, hydrogen's a very stable element, very stable element, because it only has one electron. But if you get into the really high atomic numbers, like uranium, and I believe its atomic number is 238, uranium's a very highly radioactive element that's used to, make bombs and whatnot. So more radiation is released when its electrons go to the outer levels. Yeah.